Earlier, we had some notes where we did some calculations with percent composition, and we saw that we could figure that out. We could determine that if you were given the formula of a compound, you could determine the percent composition of each of those elements within that compound, and you did that as percent composition by mass. Well, we can also do the opposite, and what we can do here is we can figure out the formula if you are given the percent composition of that compound, or even if you're just given masses that are found in that compound. So what this is known as is empirical formula. And what we're going to see is we're going to talk today both about empirical formulas and molecular formulas. The first thing you need to realize is that an empirical formula is going to be the simplest ratio for a formula. And it's going to be the smallest whole number ratio of the elements in that compound is what we have written up here. So the empirical formula is always the simplest, which means, and you have this written somewhere in your notes, if you had something like hydrogen peroxide, and the way we would write hydrogen peroxide is H2O2, is that possible for that to be an empirical formula? What do you think? No, it's not, because this is not the simplest whole number ratio. You guys could probably look at that and see that the simplest whole number ratio of that would just be HO. So yes, this is an empirical formula. This happens to be the molecular formula. So that's what we're going to end up seeing here. Is it possible for something like HO to also be a molecular formula? Yes. So it works in that direction, but not in the other. You just need to remember that the empirical formula is the smallest whole number ratio. So now when we go through these calculations, you're going to see that sometimes you're told percent composition. So if you ever start with percent, then what you need to do is you need to assume that you're starting with a 100-gram sample, and those percentages are actually going to be the grams that are given to you. So also on your notes in front of you, you have this whole list of rules that you're going to follow. I'm not going to really read through all of these. Let me just highlight a couple things. What we're going to do is we're going to calculate grams. We're going to convert grams to moles is the first thing. Then you're going to, once you've done that for each of your elements, you're going to divide each of those by the smallest number that you have just calculated. You're going to divide those. And then once you've done that, if they're whole number ratios, whole numbers, then you're just going to use those as your subscripts in the formula. If they're not whole numbers, you have to do an extra little step to be able to get it to whole numbers. So there's your list of rules. Let's see what we mean by this. So in this first example, we have a compound that gives us our percentage of aluminum, nitrogen, and oxygen. That all should add up to 100%. So we've got these three elements in this compound. We want to know what that empirical formula is for that compound. So the first thing we do is if you're given percents, remember you assume that you're starting with a 100-gram sample because you have 100%. So just assume it's 100 grams. So we've got 12.69 grams of aluminum that we're starting with, and we're starting with 19.73 grams of nitrogen. I know I've been stressing diatomics, but notice in this case, this is a compound that happens to have some nitrogen and oxygen in it. So because of that, nitrogen's not by itself, oxygen's not by itself, so you don't do the N2 or O2. You just keep it as one simple element. And then finally, we also have 67.57 grams of oxygen. So step one tells us that we are going to convert to moles. So I have to convert each of these to moles, and I know that you guys had quite a bit of practice with that last night. So 1 mole of aluminum has a mass of 26.98 grams. We know 1 mole of just nitrogen has a mass of 14.01 grams, and 1 mole of oxygen has a mass of 16 grams. So I'm going to pause and we are going to calculate. Okay, so there have been some calculations going on. We determined our moles of aluminum, nitrogen, and oxygen. We have just accomplished step number 1. So step number 2 tells us that we need to now divide each of those by the smallest number of moles that we see. So I look at that and I see, aha, right here, 0.473, that's the smallest. The reason I did that, my goal was to make one of these equal to 1, and everything else is going to be 1 or greater. So I continue with that. I divide by that smallest value. And I will just do the calculator really quickly. Also, it's worth noting that in your notes it tells you at this step, when we calculated our moles of each of these substances, it tells you go ahead and make it be about 4 significant figures. Now, ultimately, we're trying to calculate an empirical formula. So significant figures aren't going to play a role in those subscripts for the formula, but if you bring it out to a good amount of sig figs, then it's going to make it easier for you guys as you're trying to calculate some things. So I go through this, I divide 1.408 by 0.4703, and I get 2.994, that's what comes up. And for the last one here, I get 8.979. Now, by doing that, I should be able to round this to 2 sig figs and get a whole number. And obviously, I did with my first one. And I look at 2.994. Yeah, that rounds to 3.0, so I'm going to just call that a whole number of 3. 8.979, that rounds to just 9.0, so I'm going to call that 9 in that case. Okay, so again, just by doing a lot of sig figs, you're able to see, does it really round to a whole number? So you guys have just done step number 2, and our last step is now to use those values as subscripts in your formula. Now, this first example that I'm showing you is actually a little bit tricky. Our empirical formula, that's what we're doing in this last step, is we're just going to say we've got aluminum that has a subscript of 1. Well, we all know that you don't write a 1 for a subscript. It's just implied. Then N3O9. Knowing what you know about nomenclature, can you look at that and actually change that around to the right way, the correct way that it should be written? What do you think? Okay, say it louder. Okay, good. So what we see is that it's actually going to be AlNO3. So you've got 3 nitrates in that case. It's aluminum nitrate is what you've got. Okay, so most of the times we don't have that issue. Most of the things that we work with, or a lot of them anyway, are covalent substances. But when you have ionic compounds, you might have to think about that with your polyatomic. So just do the best you can. I don't think I'd take off for that. I don't know, but really work on making it the correct answer there. So that would be known as aluminum nitrate. Next one. Same sort of thing, but now instead of being given percentages right up front, we're being given grams. So we don't have to assume it's out of 100 grams. We can just start with what we've got. And we know we've got 171.0 grams of chromium. And we have 79 grams of oxygen. Again, our goal is always to convert to moles. That's our first step. So looking at your periodic table, you see that there's 52 grams for every 1 mole of chromium and 16 grams for every 1 mole of oxygen. Do a little math, and I'm just going to do this. I know you guys can plug this into your calculator. But we come up with this, and it's really even more correct as I'm showing my work. Sometimes I kind of skip over this, but if I were to write moles, because we have just calculated moles of our chromium and oxygen. So step 1 is done. Step number 2, what should we divide by? There we go, 3.288. Well, I can do this one in my head, and then the other one, I plug it in. And I don't know if that's, there's 3 sig figs. I'm not sure if that was also 4, if it was 0, 0. Yeah, so we look at that and we say, yeah, there is no way that rounds to a whole number. When I look at it to 2 significant figures, remember that's kind of your frame of mind should be to look at it as two significant figures. And is it a whole number or not? And this one is not. So this is an example where we have to do another little step. What do you think that step might be? It tells you what to do. Multiply by 2 in this case. So it might not be 2. You have to look at that number and think about what you need to multiply it by in order to have it be a whole number. So it's not possible for me to just multiply this one by 2. If I multiply this one by 2, I also have to multiply this one by 2. So our values, 2 and 3. Now for the easy part. And you guys know enough about nomenclature to know that yes, chromium is the metal, so that would be listed first, and oxygen's the non-metal, so that should be listed second. But also, the way it's listed here in your problem, hopefully I always keep it in the correct order, but just in case I don't, just think about that. So Cr2O3. Just for fun, what is the name of that? Using the stock system, what would you call that? Chromium 3 oxide. What if you use the old system? What would you call it? Chromic oxide. Okay, good. Okay. Yeah, we learned that. Chromic. We learned that. Okay, we're going to go ahead and now move on to molecular formulas. Now, the thing about molecular formulas is that the very, very first step is that you have to calculate the empirical formula. So what we've just done has to be done again for molecular formulas. Let's see what we've got here. This is where we've got our example that I just kind of mentioned about hydrogen peroxide and then the empirical formula and molecular formula. So what you're going to see is that a molecular formula is always going to be equal to an empirical formula times some value of n, okay? And where our n, it's not listed. Where is it? Do I have it on the next page? No. Shouldn't it? Somewhere. It should be on your notes. The n equals your molecular formula divided by your empirical formula. Okay, yeah, you've got it on your notes. It just didn't get on the slide here. So that's what you have to do, is you have to go through a process of calculating n. Again, n is going to be a whole number. It should be pretty simple. You shouldn't have to worry a whole bunch about significant figures to be able to determine what n is. So let's go through this example here. It says that we have 50-gram sample of hydrazine. Well, it also tells us that hydrazine is just nitrogen and hydrogen is all we've got here. The molecular mass is given to us, which is a good time for me to come back and just let you know that this, by the way, and I really didn't even write this correctly, it's the molecular formula's mass and the empirical formula's mass is what I should have said. So molar mass of the molecular formula, molar mass of the empirical formula. But that molecular formula's mass is always going to be given to you in the problem. The empirical formula's mass you can calculate because you're going to solve for that empirical formula, so then you can come back and calculate the mass of it. Okay, so we've got this information where, let's just go through this. We've got nitrogen, and they're found to be 43.8 grams of nitrogen. And it says the rest is hydrogen, so we have to do some math, and it becomes, what, 6.2? 6.2 grams of hydrogen. Okay, so hopefully you guys were following along with that. We had 50 grams total, with 43.8 being nitrogen, so the rest of it's hydrogen, which is 6.2. So again, our first step is to go through, calculate the empirical formula, so we have to convert to moles. We plug that in and get 3.126 moles of nitrogen and 6.139 moles of hydrogen. And just like we did with empirical formulas, that's what we're working on right now. So then we divide each of these by our smallest number, which is the 3.126. So step 1 is done. Step 2 is to so we got it into moles. Step 2 was then divide by by the smallest. And then step 3 is to figure out that empirical formula by using those values as subscripts. Uh-oh. Oh, yeah. Yeah, it's that tough math. Okay, thank you, everybody, correcting me here. So what we've got is our empirical formula is NH2 on that one. Okay, so we got that. So now what we have to do is we have to look back and see that it tells us our molecular mass of hydrazine is this value, 32 grams per mole. This is the empirical formula. We can figure out the mass of that. So what we want to do is we want to calculate N is going to be the molecular formula's mass divided by the empirical formula's mass. Remember, molecular formula's mass should be given to you. Do you think molecular formula's mass will ever be smaller than the empirical formula's mass? No, it is not possible because your empirical formula is your smallest ratio. So you know that you're always going to get a whole number that's 1 or greater, right? So molecular formula is 32. I'm going to write my units this one time, but after this I'm not going to. It's grams per mole divided by, how do I figure out my empirical formula's mass? You just calculate it. You add it up. You look at your periodic table and you say right here you've got 14.01 plus 1.01 plus 1.01. So you end up getting 16.03 grams per mole. So you can see that the units really end up just canceling out. It's the numbers that we're concerned with right now. So when you divide that, I'm not even going to plug that into my calculator. I'm just going to say, yeah, that's a whole number. That's 2. I expect it to be a whole number. So now, our last little step, our molecular formula, we multiply our empirical formula through by 2. So don't use big coefficients or anything. Actually multiply it through. So what do you have? You have N2H4. That is it. Yeah, no, and don't do NH2 parentheses 2. I guess that's what is more common to do instead of trying to throw a coefficient in front, but actually multiply it through. Okay. So next one. Here, same sort of deal. It's just a little bit lengthier because we have 3 elements now. So I'm going to try and whip through this. We're starting with 7.2 grams of carbon and 1.2 grams of hydrogen and 9.6 grams of oxygen. So we calculate our moles. I bet you've started memorizing some of these masses, whether you want to or not. Okay, so then we calculate and we get 0.5995 moles of carbon, 1.188 moles of hydrogen, and 0.6, I don't remember, I think it's probably 6000 moles of your oxygen. So we're going to divide each of these by the smallest number. You can probably figure out what's going on here. So this ends up being 1, this ends up being 2, and this ends up being 1. I think in the calculator it ends up being something like 1.0008. So yeah, that's 1. It's going to be equal to 1. Just trying to find those whole numbers. So that tells us that our empirical formula must be 1 carbon, 2 hydrogens, and 1 oxygen. So there's our empirical formula. And then now to calculate our N, We're going to say it's the mass of our molecular formula, which we read through, and there it is, 180 grams per mole, divided by the mass of your empirical formula. And you're probably getting pretty good at this now. You probably just add these up and say, you know, roughly 12 and 16 is 28, 29, 30-ish. So for your whole numbers, that's okay if you do that. Yeah, there's a few little numbers after that, you know, hundredths of numbers, but this is all we need. So it's going to be equal to 6, which means our molecular formula is equal to C6H12O6. Sweet. Get it? Okay. What do you round to on what? Here? Okay, so going back to this idea, the question is, what do you round to? Remember that we want this to be a whole number. So if you want to take the time of adding it all up and saying 12.01 plus 1.01 plus 1.01 plus 16.00, go for it. But if you're feeling a little bit, if you feel like you can, if you're asking this question, maybe you should take the time to do that. Maybe you need to just go ahead and stick with what we've been saying about molar masses and go to the 2 past the decimal. But you could probably look at that and know that this is going to be a whole number that we're going to end up getting. So I just kind of left off the .01s on those. Okay, so that is it for molecular formulas, which now brings us to hydrates. They are not much different than our molecular or empirical formulas, actually. So in this case, a hydrate, just like it sounds, has to do with water. So what it is that you have this compound that has these water molecules that are really chemically bonded to it. So some sort of ionic compound with water molecules chemically bonded. The way it is mentioned here is instead of ionic compound, and we kind of alluded to this in some past notes a few weeks ago, but remember, a salt is just an ionic compound. That's all it means. So you have an ionic compound or a salt that is followed by the term hydrate, and then you have to have some sort of prefix to determine how many water molecules you have. So it's pretty basic. What would you call this? Sodium carbonate. So we're naming our hydrate. And then what's our prefix for 10? Deca. So deca hydrate. That's all you need to do to name these, is you're just naming that ionic compound, and then you also have to name the water molecule afterwards with the prefix by saying a prefix in hydrate. Okay, what if we worked in the opposite direction? Copper 2 sulfate tetrahydrate. Well, the first thing is copper 2 sulfate, which really, you guys are quick at this now. CuSO4 plus 2 minus 2, so that's what it looks like. Copper 2 sulfate. And now we're going to put this dot right there in the middle. It's kind of like a times, but that's showing that it's chemically bonded to tetrahydrate. So what does that mean? 4H2O. So our 4 is not subscript. It is actually a large coefficient. So that's all we've got going with hydrates. We should be able to calculate the formulas for them also. These are just like empirical formulas, except instead of doing individual elements, you're doing the ionic compound and you're doing the water molecule, and that's it. So here it tells us the moles of water molecules that are present must be whole number multiples, so that's nice and easy for us, of the moles of the salt present. You're always going to have more water molecules than the salt. Okay, so very similar to working empirical formulas. Here we have 10.407. Oops, I'm not writing this down correctly. I have to read through my problem. This is giving me my total mass of my hydrate. So it says the sample is heated to drive off the water, and the dry sample has a mass of this. So what is that the mass of? Just the salt. So we've got 9.520 grams of our barium iodide, +2 -1. So that's how you write it. Okay, looks very similar to an empirical formula. What else do we need to do? We've got our salt. We also need to figure out the water, right? So how would you figure out the mass of your water? Subtract it. Yeah, so our total minus our salt gives us 0.887. So hopefully everybody saw that we just took this value and subtracted our 9.520. And we've got that many grams of our water in there. So we know 1 mole of barium iodide. We add that up ever so quickly, and we get 391.13 grams. And 1 mole of water, you might start memorizing this, is 18.02 grams. So when you go through the math, you get 0.02434. Sorry for the messiness. And 0.04922. Those are moles of barium iodide and moles of water that we just got. So step 1 has just been done. Step 2, divide each of those by the lowest number, which you expect to be the salt. So we get a 1. And when we do this one, you can probably even look at that without doing the calculation. You get a 2. So when you write this down, I'm going to write it up here. How would you write that? BAI2 dot, and then your 2 waters. 2 water molecules. How would you name it? You got it. Okay. Barium iodide. I can't spell. Iodide dihydrate. Fabulous. That is it. So we are going to call this quits on this, and thanks for listening.